Hi again and welcome to Embedded Systems course, Prototyping with Arduino Uno. Today, you will learn how to design a combinational logic circuit and implement a simple automation for light bulb and door lock using only basic logic gates. To be specific, you will learn everything about logic gates, like its logic expression, symbol, and truth table. You will learn how to manually design a combinational circuit using the standard forms of writing equation. We'll review the Boolean algebra, laws, rules, and theorems that you've learned in your discrete math and use it to simplify our circuit design. Finally, we'll implement the circuit using breadboard together with some additional components such as photoresistors and relays so that you can see in actual how the logic circuits can be used to control electrical devices. In this activity, we will be needing the following materials: a breadboard and a couple of connecting wires, 3 LEDs, the 7408, 7432, and 7404 logical AND, OR, and NOT IC packages respectively. We also need a 5-volt power supply. You can use either a 9-volt battery, your Arduino board, or your cell phone charger. For these demonstration purposes only, I will also use several electronic components like photoresistors and transistors, as well as some electromechanical components like these relays and solenoid, and of course, this light bulb. You don't need to have these additional components for you to understand and implement the combinational logic circuit that we are going to design. So, let's begin. Logic gates are the basic building blocks of any digital system. And if you are interested in understanding how the internals of your computer system works, then learning this topic is very vital to widen your understanding of computer architecture, microprocessors, microcontrollers, and embedded systems design. A digital logic gate is an electronic circuit which makes logical decisions based on the combination of digital signals present on its inputs. Digital logic gates can have one or more input signals that are usually represented with variables A, B, C, D, and so on. But generally, logic gates have only one digital output signal. The most basic of all the logic gates is the NOT gate. NOT gate accepts only one input signal of either logic 0 or logic 1 represented by this variable A and produces only one output signal X, which is the complement of the input signal A. That is, when the input signal is at logic 0, then the output signal is at logic 1. And when the input signal is at logic 1, the output signal is logic 0. This table is what we call the truth table, as it shows all the possible input combinations of the given logic gate or circuit with its corresponding output depending on the input condition. In electronics, a triangle is used as a buffer symbol, and the circle denotes an inversion. So basically, the symbol of NOT gate is often referred to as inverting buffer or simply inverter. And to represent this gate in Boolean expression, we can simply say that the output X is equal to NOT A or the inverted signal of A. This bar on top of the variable denotes inversion in Boolean expression. The logic OR gate is another type of digital logic circuit whose output goes high or logic 1 when one of its input signals is at logic 1. For an OR gate to produce an output of logic 0, all of its input signals must be at logic 0 as well. An OR gate circuit can have 2 or more input signals, but it has only one output signal. This is the truth table for a 3-input logic OR gate. We can determine the number of input combination using the formula 2 raised to n, n being the number of input signals. Thus, 2 raised to 3 gives us 8 possible combinations, starting from 000 up to 111. So regardless of the number of input signals, a logic OR gate will still produce logic 1 whenever there is a presence of logic 1 in one of its input signals. However, available commercial logic OR gates usually come in 2, 3, or 4 input line IC packages. So, in a 2-input OR gate using variables A and B, and an output variable X, the Boolean expression used to represent an OR gate circuit is A plus B. We use the plus symbol to denote logical addition. Same with OR gate, an AND gate is a digital logic circuit that can have 2 or more input signals and produces only one output signal. However, Logical AND gate produces an output of logic 0 when one of its input signal is at logic 0. It will only produce an output of logic 1 when all of its input signals are at logic 1. The Boolean expression for a logic AND gate is A.B. AND operation is denoted by this dot symbol as logical multiplication. In most occasions, the dot symbol is removed and a logical multiplication symbol dot is implied, as in AB instead of A.B. These individual basic logic gates can be connected or cascaded together to form a logic gate function with any desired number of inputs, or to form a combinational and sequential type circuits, or to produce a different logic gate function from that of the standard basic logic gates. In fact, there are other logic gates that exist on top of these three. We have the NOR gate. This gate is derived from inverting the output of an OR gate to reverse its function. Thus, the resulting Boolean expression for a NOR gate is A plus B over bar. Same with NAND gate, which basically means not AND, derived from inverting an AND gate to reverse the logical AND function. Thus, its Boolean expression is A.B over bar. These two are called universal gates because they can function as other gates. But for this lesson, I will not expound on this part. It is also worth mentioning the exclusive OR gate and the exclusive NOR gates. Exclusive OR gate is a derived gate from the combination of the three basic logic gates. Although the logic expression used in exclusive OR gate is this plus symbol with an outer circle, but the expanded Boolean expression of it is derived from the combinational circuit that is A bar dot B plus A dot B bar. However, the exclusive NOR gate has an equivalent combinational circuit of this, which produces a Boolean expression of A bar dot B bar plus A dot B. I will not be elaborating on these gates as well. For now, all you need to know is that these gates are not basic in nature and are derived from combining the three basic logic gates to produce a function that is very useful in most computational circuits. Now, the goal of this lesson is for you to learn how to design a combinational logic circuit using only these three basic logic gates, AND, OR, and NOT. Suppose we want to design a combinational logic circuit that accepts three input signals. We'll represent it with these variables A, B, and C. And we want that this circuit produces an output signal that controls the automatic on and off of the light bulb represented by this variable X, as well as to control an automatic locking and unlocking of the door represented by this variable Y and Z. To demonstrate it in actual, I'll be using this small 5-watt 220-volt altar bulb. This will be plugged into a 220-volt AC outlet, and I've cut one of the wires that closes this AC circuit. And like a typical switch, when these two wires come into contact, the electricity flows and the bulb emits light. And to simulate the door lock, I'll be using this 5 to 12-volt DC push-pull electric solenoid. This requires two wires to either push or pull anything depending on the polarity supplied to its two pins. So, in this instance, I'll be using two output variables X and Y to control the solenoid in both directions. To make it more realistic, let us say that the three input signals are as follows. Input A represents the main switch to activate or deactivate the device. Inputs B and C represent the two sensors that are sensitive to varying light intensity. I have a separate discussion for this light-dependent resistor circuit explained in detail in Lesson 6 of this course. For now, all you need to know is we are going to use this sensor circuit as an input signal to our logic circuit, which means the sensor will produce either logic 0 or logic 1 depending on the light intensity of its surroundings. Say, during daytime, where we have bright surroundings, this light sensor will produce logic 0. And during nighttime, where the surroundings dark, this light sensor will produce logic 1. To start designing the combinational logic circuit, we must first plot all the possible conditions of our input and output signals in a truth table. So, if we want to have a circuit that accepts three input signals, then we have 8 possible input combination. And then, for each input condition, we must specify the output logic of either 0 or 1 depending on what we want to achieve. So, assuming that this is the scenario of what we want to achieve with our simple automation. When the main switch A is at logic 0 or deactivated, then regardless of the status of inputs B and C, these are the light sensors, the light bulb X should turn off or set to logic 0. And then the door must be unlocked. Say one of the pins of the solenoid will receive ground and the other pin will receive 5 volts. This puts the solenoid in a push state simulating the unlocked door. However, when the main switch is activated or switched to logic 1, then regardless of the status of the two light sensors, the solenoid must reverse its state into pull state simulating a locked door. In addition to this condition, the light bulb will only turn on as long as the main switch is activated and at least one of the light sensors detects dark surroundings, assuming nighttime. So, to design this circuit, we must generate a Boolean expression out of this given truth table. And to do that, we have two standard options in writing Boolean expression of any given truth table: the sum of products or SOP and the product of sums or POS. Either of these two, the same functionality of the circuit can be achieved. Say I want to use the sum of products or the SOP expression to create the circuit. Note that we must create a Boolean expression for each output variable. I'll start by identifying all the product terms first, so that we can sum or add it later to produce an SOP expression. Let me start with output X. To get the product terms, or most commonly known as min terms, we must look for all the output with logic level of 1 and derive each product term. But how do we do that? I'll give you a quick and direct explanation. If we based solely on the unique behavior of logical AND gate, recall that it will only produce logic 1 when all of its input signals are at logic 1. So if we have inputs A, B, and C at 1, 0, 1, then to produce an output X of logic 1, using an AND gate to derive the product term, we should have all the inputs A, B, and C to be at logic 1 as well, as in A, B bar, C, inverting only the value of B. And for the input condition of 1, 1, 0, then the product term should be A, B, C bar. And finally, the input condition of 1, 1, 1, then the product term is simply ABC. Now, these three product terms, when added using logical OR, produce this what we call sum of products or SOP expression. We can implement this Boolean expression to an equivalent combinational logic circuit right away like this. This circuit is made up of three 3-input AND gates to produce the three product terms, AB bar C, ABC bar, and ABC. And then, using a 3-input OR gate to sum these three product terms, producing only one output signal X. Now, even though we can implement this circuit diagram on breadboard or an actual printed circuit board, this circuit can still be simplified by applying the laws, rules, and theorems of Boolean algebra. I'll give you a quick summary of Boolean algebra, but from the perspective of the three basic logic gates. First is the NOT rule. If I have an input signal, A, passes through a NOT gate, the signal is inverted and the expression becomes A bar. If this signal A bar again passes through another NOT gate, then the Boolean expression becomes A double bar. And obviously, the output signal is now the same as the original input signal. Thus, we can say that A double bar is simply equal to A. This is commonly known as double negation. I will not focus on the different terminologies here, but instead, I'll give you all the Boolean algebra principles that you need to understand based on the basic logic gates rules. The following rules are based on OR logic gate. For the logical OR rules, we have 4 possible scenarios. First, if an input signal A is ORed with logic 0, then the output signal is simply equal to A, as in, if A is 0, then 0 plus 0 is equal to 0. If A is 1, then 1 plus 0 is equal to 1. The second is, if an input signal A is ORed with logic 1, then the output signal is equal to logic 1. In a logical OR operation, presence of logic 1 in one of its input signals produces an output of logic 1. Third, if an input signal A is ORed with the same input signal A, then the output signal is the same signal as A. Finally, if an input signal A is ORed with its inverted signal A bar, then the output is logic 1, as in 0 plus 1 is 1 and 1 plus 0 is 1. For the logical AND rules, we also have 4 possible scenarios. First, if an input signal A is ANDed with logic 0, then the output signal is equal to logic 0 as well. The second is, if an input signal A is ANDed with logic 1, then the output signal is equal to A, as in, when A is 0, then 0.1 is equal to 0. When A is 1, then 1.1 is equal to 1. The third is, if an input signal A is ANDed with the same input signal A, then the output is the same signal A. Finally, if an input signal of A is ANDed with its inverted signal A bar, then the output is logic 0. On top of these rules, the general laws of algebra still apply: the commutative, associative, and distributive laws. Most often, you'll encounter an expression that looks something like this: A plus AB. You can instantly say that this is equal to A. How did it happen? By applying the distributive law, we can rewrite this expression as A quantity 1 plus B. And then, based on OR rule, 1 plus B is simply 1. And then, by applying the AND rule, A.1 is simply A. If you want, you can verify the truth table of this circuit to prove that the expression A plus AB is simply equal to A. Now, aside from the laws and rules, we also have this what we call theorems. Consider this given circuit. The equivalent Boolean expression of this is A plus A bar B. This is somewhat similar to our derived rule shown previously, but actually they are not the same. You cannot factor out A because they represent different signals. In fact, you cannot apply any rules here to further simplify this expression. But if we investigate the truth table of this circuit, you will realize that A plus A bar B is similar to the behavior of OR gate. Thus, we remove this AND gate component and this inverted signal to produce a simplified expression of A plus B. This is what we call absorption theorem. And finally, we have the De Morgan's theorem. Again, no rules can be applied for these two logic expressions. But these two circuits can be transformed using the concept of bubble pushing. A plus B over bar can be rewritten as A bar dot B bar. And when you push a bubble to apply to its individual variable, the OR gate must be changed to AND gate. You can verify that the truth table for these two expressions are the same. Similarly, A.B over bar can be written as A bar plus B bar. Again, pushing the bubble changes the AND to OR and the OR to AND. So, what now? Using these laws, rules, and theorems of Boolean algebra, we can reduce or simplify any complex expression or circuit into a more efficient and manageable one. Let's go back to our previously derived SOP expression, and when simplifying Boolean expressions, there is no specific rule to follow on which laws, rules, or theorems to apply first. You can apply anything that you can think appropriate for any given expression, so long as you can reduce or eliminate variables, making your final expression shorter. So for this expression, I can apply the distributive law to these two terms by factoring AB, quantity C bar plus C. Then, by applying the OR rule to this C bar plus C, makes it logic 1. And then, by applying the AND rule to AB.1, makes it AB. With the remaining terms, I can factor again A, then quantity B bar C plus B. By applying the absorption theorem to this B plus B bar C, results to an expression of only B plus C. You stop when you can no longer simplify the expression. Although this expression A quantity B plus C is already simplified, but we can still apply the distributive law to follow the standard form when writing an SOP expression, as in sum of product terms. Thus, this expression gives us a final simplified circuit that looks something like this. And now, depending on your need, you might want to create a circuit using the product of sums or POS instead of SOP. Regardless of which one you use, both circuits should produce the same function. For discussion purposes, I'll show you how to derive a similar function using product of sums. So, for this instance, we must look for the output signal X that has a value of logic 0, and write the corresponding sum terms, or commonly known as max terms. Sum terms can be achieved by using logical OR as the basis. An OR gate will only produce a logic 0 if all of its input signals are at logic 0. So, with inputs ABC at 0, 0, 0, then X will be 0 when we have A plus B plus C. At input condition 0, 0, 1, then the sum term is A plus B plus C bar. At input condition of 0, 1, 0, then the sum term is A plus B bar plus C. At 0, 1, 1, the sum term is A plus B bar plus C bar. And finally, at 1, 0, 0, the sum term is A bar plus B plus C. Then, to generate the product of sums expression, we need to AND or logically multiply all the sum terms, and as you foresee, the resulting circuit for this POS expression is quite huge as compared with the SOP expression because of the number of zeros present in our output X. But similarly, we can apply Boolean algebra to simplify this expression in order to reduce the circuit. First, let's apply distributive law to these two terms. A that A is A plus AB plus AC bar plus AB plus B that B is B plus BC bar plus AC plus BC plus C that C bar is 0. And now, if I factor out A, then we'll have quantity 1 plus B plus C bar plus B plus C. Similarly, I'll factor out B, and the remaining terms will be quantity 1 plus C bar plus C. Now, any signal ORed with logic 1 is automatically logic 1. So basically, this expression can be simplified to only A plus B. If you observe carefully, you really don't have to distribute each term before you can simplify it. Notice in the first two terms, A plus B is common, and C appears to be complemented and uncomplemented form, so C is eliminated. Similarly, we can apply the same concept here. Consider term 3 and term 4. A plus B bar are common in both terms, and C appears to be complemented and uncomplemented. Thus, we eliminate variable C, leaving us with A plus B bar. We can apply the same concept here as well. Quantity A plus B and quantity A plus B bar. So, by simply looking at it, B is eliminated. Thus, the simplified expression is only A. And finally, if we distribute A to the remaining terms, we have A that A bar equals 0, and the remaining terms are AB plus BC. And we arrive at an exact same Boolean expression with our SOP. But since this is in POS form, I'll factor out A to properly express it in product of sums. For the outputs Y and Z, you can try using either SOP or POS to derive an expression, then apply Boolean algebra to simplify it. You'll surely arrive to a simplified expression of Y equals A and Z equals A bar. In fact, by just simply looking at the truth table, you can easily generate a simplified expression for these two output variables, Y and Z. And finally, we can draw the simplified combinational logic circuit for our simple automated light and door lock like this. And now, for your most awaited part, let's implement this on breadboard. Standard commercially available digital logic gates are available in two basic families or forms. TTL, which stands for transistor-transistor logic, such as the 74 series, and CMOS, which stands for complementary metal oxide silicon, which is the 4000 series of chips. This notation of TTL or CMOS refers to the logic technology used to manufacture the integrated circuit, or IC, or commonly known as a chip. For this circuit implementation, I'll be using the 74 series of these TTL ICs. The 7408 consists of 4 logic AND gates. The 7432 consists of 4 logical OR gates. And the 7404 consists of 6 logical NOT gates. Each gate can be used independently of one another, without any order of priority which one to use first. Each IC needs a 5-volt source at pin 16 and a ground at pin 7 for it to operate. In digital electronic circuit, only 2 voltage levels or states are allowed. These states are generally referred to as logic 1 and logic 0, or high and low, or true or false, but technically, this terminology of logic 1 and logic 0 physically refers to the input and output voltage level the IC can recognize. For example, in a TTL IC, voltage levels from 2 volts up to 5 volts are considered as logic 1, while 0.8 volts down to 0 volt is considered as logic 0. The voltage region in between these two voltage levels, either as an input or as an output, is called the indeterminate region. And operating within this region may cause the logic gate to produce an inaccurate result. First, I'll connect the input A to one of the inputs of this first AND gate, and then the inputs B and C to the first OR gate. Then the output of this OR gate is used as an input to this AND gate together with the input A. And for its output on pin 3, I'll simply use an LED to determine its output state of either logic 1 or logic 0. If you want to review on how to connect circuits components in breadboard, please review our previous lesson, Lesson 1, Breadboarding Basics, Series and Parallel Circuits. The output Z is simply A bar, so I'll tap into this input A and invert it using this first NOT gate. I'll connect an LED as well to the output pin. However, output Y is simply equal to A. Now, instead of connecting an LED directly to this input signal, I'll use a current limiting resistor so that our LED will not burn out or get busted by receiving a direct 5-volt supply. To power this board, I'll use my cell phone charger. I've also cut this charging cable to pull out 2 wires for 5 volts and ground, put a pin header to it, and connect it to our breadboard. And now, notice that at input condition of 0, 0, 0, the output X is 0, Y is 0, and Z is 1. This condition supposedly turns off the light bulb and unlocks the door. And regardless of the input values of B and C, the output signals remain the same so long as the input A is set to logic 0. This is our main switch if you recall. And now, at 1, 0, 0, the main switch is activated and the outputs Y and Z invert its signal based on our truth table. This simulates the locking of door. However, the light bulb is still off, and it will only turn on if one of the light sensors from inputs B and C detect dark surroundings. At input 1, 0, 1, the light bulb turns on, as well as at input conditions of 1, 1, 0 and at 1, 1, 1. And as soon as I turn off the main switch back to logic 0, the light bulb again turns off and the door is unlocked, regardless of the light sensor value. So, if you're following along, then congratulations, you have successfully implemented your first combinational logic circuit design. And to make our simple automation more realistic, I'm going to implement additional circuit components here. I have a separate discussion of this LDR or light-dependent resistor in Lesson 6, and for now, just simply watch as I build it. Using these basic electronic components of resistors and transistors, we now have a low-cost light sensor circuit using light-dependent resistor. Notice that as I block the light from one of these photoresistors, the corresponding LED turns on, indicating that the voltage of at least 2 volts is present. Thus, it can be recognized by our TTL ICs as logic 1. If the environment is bright, the LED turns off. Thus, a voltage level of 0.8 volts or below will be recognized by our TTL ICs as logic 0. To use these light sensors as our input signals, I'll remove this LED indicator and replace it with a wire, and then connect it to this input B. I'll do the same thing for the other sensor and connect it to input C. And again, let's test all the possible input conditions. As long as the main switch A is set to logic 0, the door is unlocked and the light bulb is turned off regardless of the value received from these two light sensors. But as soon as the main switch is set to logic 1, simulating that the device is activated, then the door is locked. But the light bulb only turns on if at least one of these sensors sense a dark surroundings. And then again, setting this main switch to logic 0 ignores the signal from the sensors, thus turning off the light and unlocking of the door. To connect this combinational circuit in an actual door lock and a light bulb requires additional electromechanical components, and it is not ideal to explain these components right now in this context. I have a separate technical discussion of these components in the later videos of this course. For now, all you need to know is that these 3 small block plastics here are what we call electromechanical relays, and this big one here is a solid-state relay. This is purely electronics. You must understand that digital circuits like this combinational logic circuit that we have only operates at lower voltage, 5 volts and below, with a lower current as well. It is primarily used only for logic control and not for driving high voltage and high current devices. However, our light bulb requires a higher voltage of 220 volts and a higher current, more than enough to get you electrocuted. In addition, although the push-pull solenoid that we use to lock and unlock the door only operates at 5 to 12 volts, but the current it requires to energize the coil that generates the electromagnet is way higher as compared to the output current that our logic circuit can supply. So, to cut the story short, we need something that our logic circuit can control, and then it can support high current and high voltage that can switch these output devices. And that is basically the use of these relays. It can be triggered electronically, and it can drive or switch devices with higher voltage and higher current rating. I'll connect this light bulb to one of these relays. Again, please do not try this part at home if you are not very knowledgeable in electrical devices. It can get you killed. When doing this, I have to make sure that the light bulb is not plugged in to the outlet as I connect this wire to the relay. The other two relays, I will use to trigger the push and pull of this electric solenoid to simulate the door lock and unlock mechanism. Actually, this push-pull solenoid is the one used in my car's door power lock. I just borrowed it. And then, to connect the inputs of this relay circuit, I'll first remove these LED output indicators because we already have LED indicators provided in the relay circuit already. And this yellow wire is the relay input for this light bulb. For this relay to work, I also need to supply its electronic components. And the moment I supplied it, you can see that the relay on output Z is activated right away, since we have an initial input combination of 0, 0, 0, which means the door is unlocked. Now, I also need to plug this to an outlet. This is for our light bulb. And, same as before, as long as the main switch is at logic 0, the door is unlocked, and the light bulb is turned off regardless of the sensor's value at inputs B and C. But when the main switch A is activated, means at logic 1, the door is now locked and the light bulb will only turn on if at least one of the sensors receive dark surroundings. Again, safety first. Do not touch this live wire on the output side of your relay. And again, same as before, putting switch A at logic 0 deactivates the device. The door is now unlocked and the light bulb is turned off regardless of the sensor value. Combinational circuit can be as simple as this or as complex as the one inside your microprocessor chips. These AND, OR, and NOT IC packages that we use only consist of about 10 transistors inside, and you can just imagine that in today's modern technology, our microprocessors, graphics processors, and AI chips already consist of tens up to hundreds of billions of transistors in a single chip. Yes, you heard it right, billions of transistors acting as tiny switches that perform millions of logical operations in a fraction of a second. And again, thanks for watching. If you learned something of value here, please click the like and subscribe button for more programming and circuit tutorials. This is Joe Edgo and hope to see you in the next video lecture.